has started. You're welcome.
As previously stated, class recording has started. Alright, so today, the first part of this unit, the first week and a half of this unit, we have dealt with mechanical waves. What makes something a mechanical wave? It needs a medium to travel through. Okay? But if you go back to our last unit, we talked about methods of energy transfer. Mechanical waves are most similar to what method of energy transfer? At least conduction, right? One runs into the next, runs into the next, runs into the next. But one of the other kinds of energy transfer that we talked about, radiation, right? We talked about going to our analogy of passing the note across the class. What was radiation in that analogy? Just throwing the note from one side to the other. Do people need to be in these seats in order for that to happen? No. Okay? So we can get energy from one place to another even if there's no matter to carry it there. The way that happens is electromagnetic waves. So today we get into energy transfer of the radiation category as opposed to conduction, which we've been doing mostly up until this point. Okay? Alright, with that being said, let's go here. Electromagnetic waves. By definition, electromagnetic waves are transverse waves consisting of changing electric fields and magnetic fields. That's what the definition of an electromagnetic wave is. I'll give you a visual here in a second. So transverse waves consisting of changing electric fields and magnetic fields. Now, the picture I'm about to show you here is a two-dimensional representation of a three-dimensional thing. So keep that in mind. It's going to look kind of crazy when I first put it up, but I'll try and explain it to you a little bit better. People watching the video probably aren't going to enjoy this part, but oh well. So, all right. This is a picture showing the structure of an electromagnetic wave. An electromagnetic wave looks kind of like this. Okay? There's like an X. And there are two waves. One of those waves travels up and down, and up and down, and up and down. Okay? That would be like the yellow arrows that are in this picture, where they kind of go up, then they come back down to the middle point, then they go underneath the middle point and come back up, then they go up and come back down. Okay? That's the yellow wave. The blue wave is moving side to side. So it goes to the right, then it comes back and goes to the left, comes back, comes to the right. They are both transverse waves, because this wave is traveling this way, right? If we talk about these being an x-axis and a y-axis, right? The wave is actually traveling along like the z-axis. Does that make sense if we do three dimensions? Okay. The reason why we don't need a medium is because these two waves will travel through each other. So it would be like this, where one goes up as the other one is going out, but then they come back together and meet in the middle. And then this one goes this way, and this one goes down, and then they meet again. And then this one goes up, and they come back together like this, down like that, up like that. Does that make sense? Sort of, kind of, maybe? So again, I know it's kind of like toilet swimming sort of thing. But that's what an electromagnetic wave is. One of those waves is an electric wave. One of those waves is a magnetic wave. They don't exist without each other. They travel through each other, and that's why they don't need a medium. All right, is that okay for starters? Okay. Let's talk more about what electromagnetic waves do. So, electromagnetic waves transfer energy without the transfer of matter, right? Just like our analogy of the note passing. It's throwing the note from one side of the room to the other side of the room, right? And, like we just stated, electromagnetic waves do not need a medium to travel through. An electromagnetic wave travels through itself. One part of it travels through the other part and vice versa. But it's still a wave, meaning that it's going to do what? It's going to transfer energy, right? And in order for it to get made, what do we have to do? A disturbance that does what?
Work.
That does work, okay? That disturbance, in the case of an electromagnetic wave, is caused by charges. Usually it's electrons, but it could be protons, okay? Those charges move. And when they move, that causes the wave. All right, ready to rack your brain for a second? Think back in the archives all the way back like before Thanksgiving. Ooh, ouch. Okay. If I told you guys to draw for me a Bohr atom, what does a Bohr atom look like? Do you remember?
Is he the newest one?
No, he's not the newest one. Okay, Emily.
Isn't it also electric clouds?
Nope, that's Schrodinger. What does a Bohr model look like? Bohr model isn't, not orbitals, it's orbits, right? Kind of looks like a solar system, right? Nucleus in the middle, circle, 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 circle. Okay? What did we say those circles represented?
The electron energy levels.
That's where they are, but they represent what?
The electron energy levels.
The electron energy levels, right? That electrons in rings closer to the middle have lower energy. As you get farther and farther from the middle, higher energy. Is it possible for the electrons to move around within those energy levels?
Yes.
Yeah. What do they have to do?
Gain or lose energy.
Gain or lose energy. If they move up the ladder, they have to gain energy. If they move down the ladder, they lose energy. All right? Are you ready for a dramatic demonstration of that principle? Ready?
Whoa.
Good.
To clarify, you just turned on the lights.
I do need like some I should have subtitles. So, turn on lights.
Turn on
All right, so here. All the atoms that are in that light bulb up there, and all the light bulbs that are in all these fixtures, right? They all have electrons. When I turn the light on, electricity goes into that electrical energy goes into that light bulb, and it causes a bunch of electrons to jump up to higher levels. Do they like being at higher levels? No. So what do? They fall back down. As they fall back down, what do they have to do?
Release energy.
They have to release energy. Now in this case, it's not in the form of heat, it's in the form of what? Yeah, I know, you said light, or light. But in this case, it's in the form of light, which is a form of electromagnetic waves. Okay? Depending on how far they jump up and how far they fall down, that will determine the amount of energy that those electromagnetic waves carry. And we'll talk about that in just a second. How do I stop this? How do I stop this release of energy? If I turn off the light, what do the electrons stop doing?
Jumping levels.
They stop jumping levels, or they specifically stop jumping which way back up? They stop jumping up. Right? But if they don't jump up, then what else don't they do? They'll fall back down, and they don't give off energy. Okay? Good there? All right. We are going to skip Roman numeral number 2 about fields. And we are going to jump all the way down to Roman numeral number 3 that says electromagnetic radiation. Okay? So we've discussed that electromagnetic radiation is the transfer of energy through space or matter. Does the matter need to be there? No. It can be, but it doesn't need to. The energy can just travel from one place to another, even if there's nothing in between. That's the electromagnetic waves part. Okay? Now, letter B, you'll notice on your outline is like seriously messed up. Like I think I forgot to copy and paste part of this slide. Okay? The important part to letter B is this. What tells us how much energy a mechanical wave carries? The height, which we call the what? The amplitude. So the amplitude of a mechanical wave tells you how much energy it carries. That is not the case with an electromagnetic wave. An electromagnetic wave
Something about electrons?
is determined by its frequency. Okay? The amount of energy that an electromagnetic wave carries depends on its frequency. You have to write this somehow. Okay? You have to know that mechanical waves tell us how much energy they carry by the amplitude, but electromagnetic waves tell us how much energy one another, right? If we increase the frequency, Maddie, what are we doing?
We're shortening the wavelength.
Because if increased frequency means what? Increased. I think you know what you want to say, you're just not sure how to say it,
Yeah.
right? If you drew an increased frequency, how many waves would you draw in a space? More waves. And if you draw more waves in the same space, how big do they have to be?
Oh, smaller.
They have to be smaller, right? So frequency and wavelength are related to one another. How are they related to one another? They are inversely related to one another, right? Greater frequency, lower wavelength, okay? So, before we move on to the next part, okay? Do you smell anything? You know what this smells like to me?
And accept the response question?
Wait, what?
This is a short answer question on your test right here. Right? It's staring at you in the face. There it is. Sounds good. This has short answer question written all over it right here. Actually, pretty much everything we've written down so far today. Can you figure out what the short answer question would be for what we've written down today?
What is the difference between electromagnetic and the regular?
What are the similarities and differences between electromagnetic waves and mechanical waves? Man, maybe you guys should study your leads. All right.
Well, greater frequency, lower wavelength, right?
Okay, are we good with this? So, when an electron jumps up 2 levels, okay, it falls back down 2 levels, and it gives off a certain amount of energy. Okay? But if it jumps up 4 levels, it's going to fall back down 4 levels. That means it gives off more energy. That doesn't show up as a taller wave, right? If we go back to this picture, these peaks and these troughs and crests aren't taller. There's more of them. Okay? Increased frequency determines the energy that an electromagnetic wave carries. Okay? Good there? All right. So let's go to some other parts of electromagnetic waves. So, speed. We talked about in a mechanical wave that speed is determined a lot by what? What determines the speed of a mechanical wave?
Distance over time.
Well, distance over time, that's how we would measure it. What determines the speed? That plays a part in it. Say it. Frequency and wavelength do play a part in it. That's how we could measure the speed. But what really determines how fast a mechanical wave travels?
How fast the
Disturbances travel.
What did you say?
How fast the disturbance, like, where is it?
Yes, what determines that? The medium that it travels through, right? We said, what state of matter generally transfers mechanical waves the quickest? Solids, right? They're real close together, okay? But that's not the case with an electromagnetic wave. What we see with an electromagnetic wave is that, first, electromagnetic waves will travel way faster than mechanical waves. The two waves that we're most familiar with, light is a form of electromagnetic waves, sound is a mechanical wave. Okay? So light traveling way faster than sound means that electromagnetic waves travel faster than mechanical waves. You've all experienced this before. Thunder and lightning. Thunder is the sound that lightning makes, right? Okay? You see the lightning generally before you hear the thunder. If you don't see the lightning before you hear the thunder, if you hear them at the same time, hide. Okay? But generally you see the lightning before you hear the thunder. Why? Because light is an electromagnetic wave. It travels way faster than sound as a mechanical wave does. Okay? How fast? In a vacuum, with no matter in the way, light will travel at 3.00 times 10 to the 8th meters per second, or 3 with 8 zeros after it, meters per second. Or to put it in some terms that maybe are more familiar to us, 186,000 miles per second. Not miles per hour, miles per second. Yeah, it's really scary. Here's why it's scary. So first, for some perspective, okay? For some perspective. 186,000 miles per second. Light, if it could travel in a circular path, which it could, it usually doesn't, light could travel around the equator of the Earth 6.5 times in 1 second. It's fast, yeah. Now, the one thing that like really trips me out when I put this number up on the board, and every time I do it, it happens. Right? So light is traveling this fast, 186,000 miles per second. But the sun is so far away from us that even traveling this fast, it still takes about 8.5 minutes for it to get here. So take this and multiply it by 60 by 60 by 60 by 60 by 60 by 60 by 60. Is that 8? Okay. Whatever. Okay. That's how far the sun is away from us.
So how long is like a light year?
Well, let's talk about that. Okay. So now, if you look out in the sky at night and you see stars, some of those stars are 10, 20, 100, 400 light years away from us. So take this number, multiply it first by 3,600, that's the number of seconds in an hour. Multiply that by 24, it's the number of hours in a day, right? Multiply that by 365, it's the number of days in a year. And then multiply that by 400, it's a lot.
So it's actually 4 years for the light.
Well, it depends on how far away the star is, but some of the stars that we see at night, especially some of the bright ones, they're seriously like 400 light years away.
So it would take 4 years for the light.
It would take 400 years for that light to get here. So we're seeing that star as it was 400 years ago.
It's dead now.
Could be. Actually, somebody brought that up this morning. They said that they saw something related to this, and they said, when you wish upon a star, just think that star might have died like 100 years ago, just like your dreams. And I said, guess what the quote of the week is going to be next week? Right now, yeah.
Who said that? That's right.
Doesn't matter. No names, please.
Why not?
They didn't come up with it, but but anyway. So that that sort of every time I put that number up on the board, it really just kind of trips me out, like how big. And consider that the universe itself is expanding at a rate that's pretty close to this number, and it's been expanding for 14.5 billion years. Yeah. Consider that the evidence suggests. What do you got?
16,070,000 or 70,400,000.
Is that 1 light year? Yeah. It's 16 billion meters.
If that was miles.
No. Did you Becca, did you do this number or did you do this number? The 800. This one? Okay. Yeah, so it's miles. So 16 billion miles in a year. And consider that, well, you could if you want to, it's meters, but consider that, and then a star that's even 5 light years away. The closest star to us besides the sun is about 4.5 light years away.
What's the name of that star? I swear.
Alpha something, but I can't remember. Sorry. Sorry, but didn't mean to let you down. All right. That number was determined by a guy named Albert Michelson. So the speed of light was first measured by a guy named Albert Michelson. Michelson actually worked really close to here. He actually worked at Case while he was doing this experiment. So when I went to Case, I lived in a dorm that was called Glazer, Laser Hall, but the dorm next to us was named Michelson Hall. Those guys were jerks, by the way, just so you know. Right? And then the guys on the other side of us, Cush Hall, they were just lame. I mean, even for Case. So anyway, that's how. But what we find out is that all electromagnetic radiation travels at that speed, regardless. Now, that speed is the speed of light and electromagnetic radiation in a vacuum. Okay? You put it in a medium, like air or water, it will slow down a little bit, but not a whole lot. Okay? So, right, all electromagnetic waves travel at the same speed, even though they have different frequencies and different wavelengths. And we will wrap it up there today. So tomorrow, we'll watch the Magic School Bus. Then we'll finish up the electromagnetic spectrum and talk about what that is. And that will get us to the end of this unit.
Is the outline online, like, that is going to be everything on the test?
So objective sheet.
Is the rest of this outline?
Yes, it is. You want to finish that?
I got the other one.